Good morning, ladies and gentlemen. We are now going to start today's program. I'm Ki-Jun Young from Sunwon University, chairing this session. And this session is co-chaired by...
Yeah, I'm very pleased to join the co-chair with Professor Ki-Jun Young. I'm currently from Dalian Institute of Chemical Physics, China. Okay.
Today is the last day, and we hope that this Congress will be ended successfully. And okay, we will have the last plenary lecture, and this will be given by Dr. Jens Norskov from Denmark. And let me briefly introduce the speaker. Could you? Dr. Norskov is a professor of theoretical physics at the Technical University of Denmark, and has been served here from 1992. He obtained his PhD in 1979 in theoretical physics at the University of Aarhus in Denmark. And he has published more than 300 papers and several patents. He is also serving as a director or chairman of several scientific centers, including atomic scale molecular design. He also received many awards and honors for his excellent scientific achievements, as well as for outstanding lectures in Denmark, as well as outside Denmark. He is also a member of many scientific committees, including the Niels Bohr Medal and several editorial boards, including Journal of Catalysis and the Journal of Chemical Physics. He recently received the Millikan Medal and became an honorary doctorate at Eindhoven University of Technology. And his research interests are in the theoretical description of surfaces, catalysis, nanostructures, and biomolecules. So we anticipate a nice talk today. Please.
Thank you very much, Mr. Chairman. Thank you for the very kind introduction. Thanks to the organizers for giving me a chance to contribute to this wonderful meeting. And what I will be talking about here is a shall we say, atomic scale, molecular scale view of what goes on at the surface during a chemical reaction. And my viewpoint is that of a theorist, but as you'll see through my talk, everything is closely coupled to experiments. You couldn't do it otherwise. So here's the outline. I'll first spend just a little bit of time discussing whether the theoretical methods we do have at our disposal now are good enough to actually treat the complex systems that we need to treat in catalysis and with an accuracy that is useful. Secondly, I will then move on to discuss how we can treat not just one system. That's interesting enough, but what is really interesting is to take a step back and look at a number of systems to figure out why is one catalyst better than another one. And I'm going to introduce some concepts there to make it easier to think about these things and to do the calculations. And then finally, I'll be discussing how one may be able to use this insight and these concepts in finding leads for new catalysts based on theory, but again, combined with experiments. So first, the question of complexity and accuracy, and I'll start with the accuracy. So if you'll bear with me, just one slide with a table here, just indicating the kind of accuracies you can expect from density functional theory calculations, which is what we're using and what essentially everybody is using these days. And what you see here are mean absolute errors for a series of molecules. These are binding energies of the molecules, and for a series of adsorbate systems, and the errors are relative to experiment where they are available. And you'll see three different kinds of treatment of electron-electron interactions. The first that was introduced by Kohn and Sham back in the 70s, the local density approximation, LDA. And you can see that the errors are enormous. 1.5 EV, that's about 150 kilojoules per mole, and it's really, that was the reason why this was not very useful for chemistry. What happened in the early 90s was that there came a number of different alternative methods, and here's one, PBE, developed by Purdue and Becker and Erzenhofer. And what you see here is that the errors are reduced substantially. And with the last version of that, we are now down to errors that are of the order 0.2 EV, 20 kilojoules per mole. Bear that in mind. Is that useful? I'll try and illustrate that it is by looking at some concrete examples. So, for instance, if we try to describe trends in adsorption energies, we're doing very well. This is a comparison of oxygen adsorption energies, and this is the heat of adsorption, so negative means strong bonding. This is a compilation by Gabor Sommerjai some way back for all the 4D metals. And you can see that when we do the calculations, we actually describe all the variation in the oxygen binding energy very well. So we do trends quite well. But of course, if you look at the energy scale here, it is quite large. So 0.2 EV wouldn't show up here. But if we look at relative energies, small energy differences, our accuracy is actually much better. This is a comparison to experiments done in the group of Jürgen Behm. What he did was to do experiments, combined STM and thermal desorption spectroscopy for CO adsorption on a number of different surface alloys, and he was able to distinguish between all these different adsorption sites and find the desorption temperature for those. We did calculations for the same systems, and here's a comparison of the calculated adsorption energy on the y-axis and the measured desorption temperature. And what you see here is that for the relative binding energies, we're doing much, much better than 0.2 EV. I mean, now we're talking about a fraction of a tenth of an EV in accuracy. And that's important because a lot of what I'll be talking about is actually trends, looking at variations from one system to the next. And there we seem to have 4 systems like this, and let me stress that. This is for adsorption on transition metals. We seem to be doing very well. Now, what about the complexity of a full catalytic reaction, and how about rates? How do we do there? You could fear that 0.2 EV error would show up as orders of magnitude error in calculated rates. Let me illustrate how that looks. So what we did was we looked at the simplest catalytic reaction, possible ammonia synthesis. We calculated the energy diagram for the full reaction, adsorption of molecular nitrogen, dissociation of nitrogen, adsorption of hydrogen, and then sequential hydrogenation of the nitrogen to form one ammonia and a second ammonia molecule. And we will try then to do kinetics on the basis of this. The first thing to notice is that when you compare the dashed, which is for a closed packed surface, and the full line, which is for a step, you'll see here clearly that steps are much, much more reactive. Barriers are way lower. In fact, they are so much lower that for this system, and actually for many systems, you can forget about the flat part of the surface for the reaction. This is not always true, but this is the case for reactions like this. This has been confirmed experimentally, and I think this is actually one of the great, or one of the early really big successes of these calculations, that we're actually able to figure out that everything is happening on the steps for a reaction like this. Now, what we do is we use all the barriers here, calculate rates, but we do it not just for a single system. We include all possible local configurations of the dissociating molecule, for instance, on the surface. We calculate not just activation barriers, but all pre-exponential factors in harmonic transition state theory. We include adsorbate interactions and do Monte Carlo simulations to have realistic views of how the surface looks at reaction conditions. And then we want to compare to a real catalyst, a nanoparticle supported catalyst, this ruthenium, and our colleagues at Adsorption have done both the experiments, Søren Dahl here, and for the reactor experiments, the kinetics experiments, and they have also done, Anna Karlsson here, the TEM. And this is a TEM of the very sample that where they've also done the kinetics, and you can actually see the step atoms where the catalysis takes place. You can't quite count them, but through a procedure, we have been able to figure out a rough estimate, at least, of the number of active sites. And that's all we need in our kinetic model in order to be able to compare directly to experiment. And when we do that, with no fitting, no nothing, then it looks like this. So this is now comparing DFT results directly to measurements in a plug flow reactor at 50 bars and realistic conditions. Here are results, ammonia out of reactor as a function of temperature, and here as a function of flow. The upper one is the measured, the lower one is the calculated, and you'll see that there's actually a fair agreement. Certainly much better than we had hoped. For large conversions, it's about a factor of 2. For low conversions, it's more like a factor of 10. But even that, we consider to be extremely well represented. And you can really ask, how can we, with the accuracy, this is a single system, with the accuracy that we have, how can we get such good results? And the reason, I can illustrate the reason in the following way, but before doing that, let me just point out that this is not a unique example. There are actually a number, and a growing number, of examples of calculated rates on the basis of density functional theory that compare very well with experiment. Here are two examples, one from the group of Matthias Scheffler and Carsten Reuter, comparing zero oxidation on ruthenium dioxide to experiments in the Ertl group, and one is experiment, one is theory. I don't even remember which is which, but you can see here that it doesn't look too bad. And here is some work done in Madison, Wisconsin, Manos Mavrekakis, Jim Dumesic, measured rates of methanol decomposition on platinum. Here's the calculated, and here's the measured turnover frequency. Very, very good agreement. And again, why? And getting back to the ammonia synthesis, then here is one part of the explanation. What we've done here is we've calculated the rate of ammonia synthesis, the turnover frequency, not just for ruthenium, but actually for a number of metals. And we plotted it as a function of the dissociative chemisorption energy of nitrogen. And well, first of all, you notice we do actually get the trends right. Ruthenium best, osmium then, iron, and so on. That's exactly what has been measured experimentally. But that's not really the point here. The point is that you have such a volcano. I'll get back to that in more detail later. And the reason is, of course, that on one side, when you get to too weak nitrogen binding, N2 dissociation gets too slow, and too strong nitrogen binding, you just cover the whole surface with nitrogen and nothing happens. But the point is that right here at the top, even a relatively large error in our calculated nitrogen binding energies, for instance, is not going to give rise to a large error in the rate. That's a compensation effect right there at the top. So when we calculate rates and we are close to the top, that is for good catalysts, then we're saved by the fact that there are several factors that compensate right at the top. If we did a calculation of the rate on nickel, we could be orders of magnitude off. But of course, that's less interesting. What we do get is that nickel is worse than ruthenium, and that's really all we're after. So let me then move to the question of how do we treat not just a single system. I can tell you one would not want to go through what we went through for ammonia synthesis for each system, and certainly not for the more complicated ones. How do we deal with many systems? And let me introduce some computer experiments that Frank Abel Petersen and a number of other students and postdocs here did. Just use the computer, generate data, and start looking at data, just like when you do experiments. What Frank did was that he calculated the adsorption energy of CHX, that is CH, CH2, CH3, for a number of different metals on different surfaces, both closed packed and stepped surfaces. There will be other structures later, and plotted them as a function of the calculated carbon binding energy. And what you see is that there are clear correlations, right? Not unexpected. If you look at these fits here, you'll see that the slope here is 3/4, the slope here is 1/2, and the slope here is 1/4. That sort of looks like a thought, right? So if you think of C being able to make 4 bonds, then this can make 3, 2, and 1. Very simple. Shockingly simple. If this is right, how about NHX? Well, here they are. NH and NH2 bond energies as a function of the N binding energy. And now the slopes are 2/3 and 1/3, as you would expect. What about oxygen? Here's OH versus O, and the slope is very close to 1/2. So there's certainly a picture that emerges here that looks interesting. Before I get to sort of what this is all about, let me just make one point here. This is the CH3 versus C, and there is some scatter, you can see that, but actually the mean average error for all these points is 0.13 eV. That's comparable actually to the DFT error. But we can actually do better, because the methyl radical, that actually usually at least binds on top of a single atom, whereas the carbon, these are 1,1,1 surfaces, binds in a 3-fold side. Those are quite different. If we actually move the carbon onto the on-top side, we can do that and do a calculation there, then, well, also alloys are not doing very well here, but if we do that, then of course all of the carbon binding energies become weaker. Right, you move to the right. This is just a difference in bond energy in the 3-fold and the 1-fold side. But the mean average error now is 0.06 eV. It's actually very accurate. And you see the alloy points are now on the line. It was simply because you have to take into account the exact local structure when you have an alloy. It really does matter whether you bond to gold or to palladium, right? So this is the kind of errors we have. And the picture that emerges is one where you have these linear relationships scaling relations between bond energies of some species, hydrogenated species, and that of the central atom. And these coefficients here are really just valency parameters. And this is really an illustration of bond order conservation. It just means that whatever bonding you don't have to the hydrogen, you have to have that to the surface. And this, of course, has been exploited extensively by Sustrovich and Alex Bell and others for many years. What about more complicated molecules? This is ethylene and acetylene, now as a function of the methyl binding energy. So methyl has one bond, right? This has two sigma bonds, and this has four. And of course, for that reason, the slope here is 2 and the slope here is 4. It's really shockingly simple, but very useful. What about other kinds of materials? Here are similar results for oxides, nitrides, and sulfides, exactly the same picture. So this is one kind of correlation. This is a correlation between the adsorption energy of one species and that of another one. We can also find correlations between the adsorption energy in a transition state and the adsorption energy in the final state, for instance, or the initial state for that matter. Here are examples. These are transition state energies or activation energies for the association of N2CO, NO, and O2 as a function of the dissociative chemisorption energy. And you see nice linear correlations both on flat surfaces and on stepped surfaces. You could say again, well, there's some scatter here. This was actually a collection of a lot of data from a lot of very different calculations done in various groups. You can see the list of authors here. Recently, we actually went back and we just took one system and we really made sure everything was converged completely, and then you actually, same structure, then you see transition state energy versus dissociative chemisorption energy. They're really like pearls on a string. What all of this means is that if we have a database of adsorption energies of a few very important atoms, we can construct adsorption energies on almost anything. What it means is these scaling laws, they mean that if you want the adsorption energy of some molecule, and it doesn't have to be just, A here could be a big molecule. It doesn't have to be a single atom. On one metal, on a metal M2, and we have the calculation on a metal M1, and we have a database of adsorption energies of the central important atom A on these different metals, then we can construct this, and this here is just a rational number that you can look up or calculate in your head. That has enormous implications, because I showed you, for instance, we had done the full calculation for ammonia synthesis on ruthenium. And here is a plot of the energy of all the intermediates on ruthenium is one of them, I don't remember, that's the light blue here, for all the different intermediates here. And then because we have a database of binding energies on a number of other metals, and here I've just taken these 12 here, then we can immediately construct the potential energy diagram for all these metals. So we get a complete overview of the energetics of this reaction on a number of different metals. And what you see here is that you can see immediately why some of the metals, all the noble metals here, will never be ammonia catalysts, right? I mean, the intermediates are so high in energy that it'll never happen. You can also see why tungsten won't work, because you'll cover the surface with nitride. It'll actually become a nitride, and then it's a different story. But this is a very simple tool. What you really want is sort of those that track the simplest possible route from the initial to the final state, and what you find in here are things like iron, ruthenium, things that are known to be very good catalysts for this reaction. Notice, by the way, that the differences between different metals, they're large. I mean, large on the scale of 0.2 eV. We can get a lot of insight from this. Here it is for another reaction, steam reforming of methane. This is now an endothermic reaction. And again, you see that some of the noble metals, or very noble metals, they will never be able to do this. And you can also see that, for again, tungsten, you'll find carbon and oxygen so strongly there that it won't be able to function. And again, some of the best catalysts are really interpolating quite well between the initial and the final state, ruthenium, nickel, rhodium, that kind of thing. I'll get back to that. So it's actually a quite powerful tool if you want to understand these things. Now, we can, of course, combine the scaling between initial and final state with also the BP relations, or the scaling of the transition states, and that way we can actually get not just energies of intermediates, but actually also barriers. And this is included, this is work done in the groups of Manos Mavrakakis and Jim Domesic at Madison, where they look at a fairly simple molecule, ethanol, and the decomposition of that. And each column here, if you can see it up here, this is the reaction energy and the barrier for the splitting of the CC bond and the CO bond. And this is actually the number of different intermediates where you can have that happening. There was one calculation done for ruthenium, then we got the rest from scaling and BP relations. And we have a complete overview now. In fact, you might say that here's more information than you really want. But I don't think that's true, actually, because we really do need this overview. Then we need methods now to figure out how to use this, that is, to zoom in on what is important and what is not important. But we can actually get the overview now. So these are quite powerful methods that allow us now to get quite detailed overview of a large number of reactions quite simply. Let me just spend a couple of minutes discussing what is the origin of all these correlations. And I'll just introduce you to a very simple picture of the chemical bond between an adsorbate and a surface. So if we have here an adsorbate state, think of, say, the 2p state of oxygen or nitrogen, interacting with the electronic states of a transition metal that has a broad S band and a narrow D band. You have Fermi level here. Then at least when you think of it, you can think of first coupling to the S band. That'll give a lot of charge transfer and coupling. But that'll be essentially the same for all transition metals. All transition metals in the metallic state have a half-filled S band, broad S band. Then you include the coupling to the Ds, and you get bonding and antibonding states. And the variations in the bond energy from one transition metal to the next is really related to whether or not you fill this antibonding state. And clearly, the higher in energy the D states are, the higher in energy the antibonding state will be, and the less electrons you will have in it. So we do get this correlation. Now, if you would like to see this borne out experimentally, here's a beautiful set of experiments done in the group of Anders Nilsson at SSRL at Stanford. And what it shows here, up here are the experiments, down here are actually the calculations. Binding energy of the electrons here, 0 is the Fermi level. And this is X-ray emission and absorption spectroscopy, so that you look at both the filled and the empty states. This is for nitrogen on nickel, which has a high-lying D state, and for copper, which has a much lower-lying D state. And you see here clearly how you see the bonding states. There are two different polarizations, don't worry about that. You see the bonding states and you see the antibonding state here. The bonding state, the antibonding state. On copper, the antibonding state is completely filled. You have a weak bond. On nickel, the bond is much stronger simply because you have depopulated the antibonding state, and you can see it very clearly. So this is really a very direct confirmation of this physical picture. And you can see it when you look at trends. So The upper panel here is what I showed you before, the SumRGI data for binding energy of oxygen on a number of transition metals. And below, I've taken the same data and plotted it as a function of the average energy of the d electrons. And you see exactly this correlation. The higher in energy the d electrons, the stronger the bond. Here's a more subtle effect, but very important one. This is a set of calculations that John Kitchen from Marc Barteau and Zhengguan Chen's group did for bonding of oxygen and hydrogen on platinum, but platinum where you had stuck another metal, a 3D metal, in the second layer. So oxygen or hydrogen always binds to platinum, but you just modify, you tweak the properties of this platinum by putting another metal below. It's a ligand effect. And you can see that as you go from nickel, cobalt, iron, as you move to the left in the periodic table, you can see how the d states are shifting down in energy. And from what I've told you, that should mean that you get a weaker and weaker bonding, and this is what you see calculated here. Bonding, you can almost tune, not continuously, discretely, but you can tune the oxygen bonding to platinum by more than 1 eV by changing the ligand of the platinum in the second layer. This is actually exploited directly, and I'll get back to that in a moment. Another example here is bonding a methyl to nickel, but these are nickel in very different states. Nickel 111, 211, a stepped surface. You can strain it, that changes things. You can adsorb carbon, that shifts the d states of the nickel so that the nickel binds weaker to something on the other side, or you can alloy it, say, with gold. In every case, you get this tracking with the average energy of the appropriately chosen d orbitals, because it has to be the d orbitals to which you bond, as you can imagine. Now, with this picture in mind, we can understand where these correlations come from, because you have such correlations for the CH3, for the, say, the CH3 bonding, but you have completely similar correlations with the D-band center for, say, the barrier for CH4 dissociation. And of course, when you combine these two linear relationships, you're bound to get a linear relationship when you plot the barrier for dissociation as a function of the binding energy of methyl, right? So what it really means is that there is an underlying parameter. The electronic structure of the surface determines both the stability of different intermediates and the stability of the transition state. And this underlying, the hidden parameter, the electronic structure factor, is really what gives these linear relationships. This has some consequences, all of these. So here's the ammonia synthesis example again that I showed you before. And there are actually, if you look here, 5 independent kinetic parameters that we should, and we do put in to the kinetic modeling. But of course, the barrier for N2 dissociation scales with the nitrogen binding energy. The stability of NH and NH2 also scale with the nitrogen binding energy. So essentially, there are only 2 independent parameters, namely the nitrogen and the hydrogen binding energy. And the hydrogen binding energy doesn't vary very much, so essentially there's only one independent parameter in the problem. That independent parameter characterizes the catalyst. And that's why we could plot the rate as a function of this parameter. This is the way of choosing the independent parameter in a volcano plot. Let me take another example. It's a totally different area. If you look at the electrochemical reduction of oxygen, as it happens at the electrode in a fuel cell, then again we can calculate the potential energy diagrams, or free energy diagrams actually here. We can do it even at different potentials. I don't want to get into that. But the point is that there are actually 4 independent, there are 4 kinetic parameters here due to the number of intermediates. But again, the stability of OOH or OH scale with the stability of oxygen, And therefore, there's only one independent parameter. And that's the reason why we can actually plot these are actually measured activities as a function of the oxygen binding energy, and we get a volcano out. This is the theoretical volcano. These are actually measured data from the group of Nenad Markovic and Phil Ross at Berkeley and Argonne. You see here, by the way, exactly this thing of tweaking. This is platinum. Here's platinum with cobalt and nickel. This is exactly the effect that I talked about before. You tweak the properties of platinum by putting cobalt or nickel in the second layer. That weakens the oxygen bond and gives you a much better performance of your fuel cell. So this is exploited very, very directly, these tweaking effects that I'm talking about. Here's another example. Steam reforming, many more steps, 16 kinetic parameters. But in actual fact, since everything scales with the carbon and the oxygen binding energy, then there are only 2 independent ones. And that means that we can actually make a model of the kinetics just based on those 2 parameters. Actually, the models here are quite simple because it turns out that there's nothing on the surface at the temperatures where this runs, and this is in complete agreement with the experiments of Iglesias' group. And what you see here is now a 2-dimensional volcano, contour plots. Red means a high activity, blue means low activity, and then each of the transition metals are put on here with the 0.2 EV error bar. And you can again see that we can say something meaningful even with that error bar, in particular close to this broad minimum that you have up here, or maximum, sorry. What you see is that according to this, the best metals are things like ruthenium, rhodium, nickel, iridium, and that is exactly what is seen experimentally. Here are some experiments from Jens Seested and co-workers at Haldor-Topsøe, and there's also TEM, in situ TEM measurements by Stig Helvig and co-workers, same place. And that means that they can measure now the rate as a function of the dispersion for a number of different metals, and you see that the ordering that we have here is actually exactly what you see in the experiment here. You see, by the way, also, if you noticed, I don't know, there's a simple way I can go back here. You notice that also for this reactions, steps are more reactive than the terraces, and you can see this directly in the, how do I then go forward? How do I go forward now? Does anyone know? Yes, now I can. This is what is reflected in the fact that there's a linear relationship between dispersion and rate. That means that it's actually the steps, the linear defects, that does it. So this is in agreement also with a number of earlier pieces of work. It's also in broad agreement with the recent work in the Iglesias group and the fact that these metals here are the most active, but there's not complete agreement in terms of the ordering here, and we need to figure that out, what is going on here. So that leads me to the final part of my talk. Can we use the insight that I've been describing here, the concepts, to make intelligent, or semi-intelligent at least, suggestions for new catalysts? And I'm going to take 2 examples to show that. But first I would like to just point out that this is really part of, let me say, a much, much broader set of issues. The question of, can we design matter on the basis of insight, on the basis of the electronic structure? And as I pointed out, the electronic structure is really what is behind all of this. What we have been, and what I've been discussing here, and what we've been working on for the last 20 years, is the question, can we, if we know the structure and composition of a certain material, can we then calculate the electronic structure, the band structure, say, This is an MOS2 slab with an edge that can adsorb something. And can we then predict, or understand at least, what are the chemical properties? It could be as an HDS catalyst or for hydrogen evolution that it's used for also. That's what we've been working on, that's what I've been trying to illustrate. But the real challenge is going the other way. Because we really need to be able to say, if we want a certain functionality, which requirements does that make to the electronic structure, and how can we construct matter that has that electronic structure? This, of course, is a problem very general in all of condensed matter and in molecules and in biological systems. I think we are in a particularly good position in catalysis because we know a lot about what goes, how we relate functionality and electronic structure because of these relationships that tells us what is the important parameter and what is not. So we may have an advantage here over many other areas if you wanted to do the same thing for, say, structural materials. You would have to worry about things that happen at many, many different length scales, and that would be very, very tedious, but still something that people are pursuing very, very accurately. So let me take a particular example. If you want to make polyethylene, you do that from a feedstock that contains typically ethylene, but also a little bit of acetylene, and the acetylene is a poison, and you want to get rid of it, and the way you do get rid of it is that you hydrogenate the acetylene to ethylene, but what you really don't want to do is to hydrogenate your feedstock to ethane, because then that's a loss. So you want to selectively hydrogenate the acetylene. And presently a palladium silver catalyst is being used, and I can show you here why, I think. And here we are following very closely some work that Matt Newrock and his group did a few years back. So the blue line up here, that's the energy of acetylene. This blue line is ethylene, and down here you have ethane. And this is the potential energy diagram for the sequential hydrogenation. First you adsorb ethylene, you hydrogenate once, twice, then you get down here. What you would now like to do is to desorb up to the blue line here and not continue down here. And you can see palladium, the first barrier here is just about the same level as the energy or the desorption energy, so palladium is at the border of being able to do this. If you add silver to this material, then everything shifts up in energy, including this barrier here, and hence you get selectivity because now the rate of desorption is considerably larger than the rate of further reaction. You'll notice here that all the barriers are basically the same, about half an EV, but what really happens when you alloy is that you shift up the stability of acetylene and ethylene. The dream would, of course, be if you could shift up this a lot and not shift up this, right? That's what we want. But that's not possible. And you have already seen why, because you have these scaling relationships. I showed you this before. Both the ethylene and the acetylene binding energies scale with the carbon to surface binding energy. And that means that you cannot make this here weaker without making this here weaker. You can make some simple estimates of where you want to be here, because if, for instance, we say that we want a turnover of the hydrogenation of acetylene of the order 1 per second, then you can easily figure out that that means that you need a binding energy of the acetylene of the order 0.3 eV, and that will translate into a binding energy of methyl of the order 1 eV. And of course, if you bind this stronger, then you'll get a higher rate. And so it means that turnover the better, the more to the left. We can also very easily see where the rate of hydrogenation of ethylene is equal to the rate of desorption. That's just where the barrier for that hydrogenation step is equal to the zero of, or the energy of ethylene in the gas phase. And that translates into a binding energy of methyl around here. And of course, if you want high selectivity, you want this to be bind weaker, and that means that high selectivity you want to be to the right of here. So there's a window of opportunity, according to this simple thinking. So it means that if we can calculate the methyl binding energy on a number of different systems, and this is work done by Felix Studt and Frank Abel Petersen here, then we can actually get an idea of some possible candidates in this window of opportunity. And let me show you the result of such a calculation. So they looked at a number of alloys containing these elements here, and each point here is now a calculation of the methyl adsorption energy for each one of them. I've indicated here the window, and it's been smeared out due to the uncertainty. I mean, we don't want to make statements that we know exactly what it should be, so there's certain uncertainty, but at least you can see where the window is, and that's good enough to pick out some possible interesting candidates. And then we also put another parameter here just to make the graph more interesting. But it is, of course, interesting that palladium is quite expensive, and if you could find something cheaper, that might be of some use. So let's look at these candidates that come out in the window. So there are a number of palladium alloys that come out: palladium silver, palladium gold, palladium zinc, palladium gallium, palladium lead, and actually all of these have been reported, some of them quite recently, in the literature to have good selectivity for this reaction. Work here, this is the original silver work by Goodman and Rodriguez and in the Slurgel group here. Now, there's also recently been a suggestion by the Slurgel group that subsurface carbon should have this effect. If you can get some subsurface carbon into palladium, then that should work. And this is increasing amount of subsurface carbon. You see it moves palladium, which is right at the border of being selective, well into the selective range, in complete agreement with their observations. And then, of course, there are a number of candidates down here that look to be much cheaper. And we focused on nickel zinc simply because it's very, very stable. It's a very stable alloy. So we did the full calculation in detail just to check that our simple interpolation or our simple scaling worked. That works fine. And then in the group of Klaus Christensen, they actually synthesized a number of these catalysts. These are results now on a magnesium aluminum spinel support. And this is outlet of ethane, so that's what you don't want as a function of conversion. So you really want to be down in this lower right-hand corner. And you see palladium, pure palladium, goes some way, but when you get too little acetylene in there, then it won't work anymore. Adding silver has a dramatic effect and really makes this look very good, and this is actually a composition close to what is used in industry. I'm not claiming this is the industrial catalyst, but certainly you can see why silver has been added in industry quite clearly here. If we take nickel, it's worse than palladium, as you would expect, as the calculations indicate. And then we start adding zinc. And if we add more and more, it gets better and better, and eventually when we get to quite a high zinc loading, we get down to something which is at least same order of magnitude as the palladium silver. So it indicates, at least to me, that we can use these computational methods to get some interesting new materials that might be worthy of further study. Let me stress that, I mean, this is not a technical catalyst. I mean, this is just a hint at something that might be worth studying. There are lots of other considerations of byproducts and stability and things like that that need to be worried about. And we're really not in the business of making catalysts. We're in the business of understanding what goes on. But there are other people that are very good at making catalysts, and we have another example here where we actually interacted with the Topsøe company that are very good at making catalysts, and where they actually took an idea and have turned it into an industrial catalyst. And this is the example of the methanation reaction, CO and hydrogen forming methane and water. Again, there are volcano relationships relating activity. This is measured. This is calculated dissociative chemosorption energy of carbon and oxygen. And in fact, we should have used both. Again, this is just the reverse of the water-gas shift. So it should be both carbon and oxygen. It turns out that this linear combination actually works quite well, as you can see here. And so we have a descriptor, and we even know where the optimum is. And then again, we looked at a large number of different alloys, and this is work with Martin Andersson and Klaus Christensen was very important here, Jeff Greeley. This is again cost here, because that is a factor, not a scientific factor, but a very important industrial factor. And down here is our descriptor. It is the difference between the dissociative chemosorption energy of CO for whatever system we look at, and that of the optimal. So we want to be as close as possible to zero here, and obviously we want to be as far down here as possible. Each point here is an alloy. The elemental metals are in black, so here's iron, nickel, cobalt, ruthenium, rhodium, and so on. So some are not only very expensive, but also very bad. Nickel is what is used. It's quite good and quite inexpensive. It is getting more expensive these days, but it is still quite inexpensive compared to the others. And this here is the Pareto optimal set that comes out of our investigation. And Pareto optimal, for those who didn't take Economy 101, is simply the set of solutions where you can't do better in one direction without getting worse in the other. So this is the best compromise between, in this case, price and activity that comes out of this simple calculation. And the knee is always very good here, because that means that when we get out here, it's really very good and still quite cheap. And you see that the iron nickel 3 alloy here looks quite interesting. It's actually better than nickel, apparently, and better than iron, and cheaper than nickel. So again, Klaus Christensen and his people made a series of catalysts. Here are measured activity, again, of a supported catalyst as a function of the ratio of iron and nickel. So this is pure nickel, pure iron, and you see how the iron nickel 3 really stands out as particularly good. That's where it left our hands, and Jens Seeste and co-workers have actually been working with this catalyst now and put it on the real industrial support, looked at the real feed. This here is on a real feed, or a better feed, including CO2 and things like that, and you see that it still performs. And this is actually a catalyst which is now in industry. So it is possible, in some cases, if you're lucky enough, I'm sure, to do things like this. So let me end by mentioning all the people who have contributed to this work. First here, a number of collaborators, students, postdocs in my group, and some of them have left, and I've indicated where they went. I won't read all the names, but I mentioned some of them along the way. We've had a very, very fruitful collaboration with Klaus Christensen and his group, both in developing some of the concepts and also in actually being close to somebody who can make catalysts. That's a very useful thing if you're a theorist. And same thing with the group of Ib Korkendorf, Tom Jaramillo at DTU. Felix Stud and Frank Abel Petersen, they have actually formed a company that does these things for industry. And they have a booth up there if you want to visit them. We've had a long-standing and very, very fruitful collaboration with Haldor Topsøe. A number of people have been involved. Jens Seest, I mentioned several times. Stig Helvig, Jens Rostrup Nielsen, Bjarne Clausen. We've had a very fruitful collaboration with Manas Mavroukakis, Jim Domesic, his group there, with Marc Barteau, Jingguan Chen, and John Kitchen, who is now at Notre Dame, with the group of Jürgen Behm, and with the group of Anders Nilsson. And so let me just summarize. We are actually able to describe complete catalytic reactions at a certain accuracy. That means that we have a credible starting point for beginning to say something about variations in activity and things like that. And in particular, we can say something about trends. We have methods for treating a large number of systems. We have developed these methods very recently, and it's really opened up totally for the number of possibilities we can look at. We have these very important correlations between barriers and reaction energies that are also opening up the possibilities of what we can look at, but also actually simplifying everything enormously to the point where we can really pinpoint what is important and what is not important. We have identified, at least for transition metals, and let me stress that what I've been talking about has been mostly transition metals. There's still a lot of work to be done for oxides, nitrides, sulfides, what have you. Understanding what it is that really determines the reactivity, at least to a first approximation. We can use this to make predictions in volcanoes, and in some cases we have actually been able to use this to make suggestions to experimentalists about where it might be interesting to look for new and better catalysts. And with this, I would like to thank you all for your attention here this morning.
Thank you, Dr. Norskov, for that nice talk. And on behalf of the organizing committee, we prepared some gift as a souvenir, I think.